Good afternoon. Welcome back for a long weekend. It's great to have everyone back here, and we're going to get started exactly where we left off. So we have been going through the different foundations of computer systems. So what we're doing here is we are going to be building up the things that you already know about, that you've already used for the entire time as a computer scientist, and give you a little insight on what's going on inside the computer. So up until now, we've talked about, in the very beginning, about data. How do we represent zeros and ones? We looked at hexadecimal, and you guys are now experts at reading and writing binary and reading and writing hexadecimal. And when you see a hexadecimal digit, you're not scared of it anymore. You've got this. And now, we've talked about the CPU. So we have talked about how you can actually take instructions, which we call opcodes, and actually see how your program compiles into instructions where the CPU executes it line after line after line after line. And now, we want to actually talk about the storage of all of this data inside your computer. So up until now, we said we've got data, and we have the CPU that's processing the data, and the data is going to tell the CPU to do things like adding, subtracting, shifting, multiplying. We have all of these different foundations, but how in the world do we store data? And this, I want to begin by talking about the memory hierarchy. So we're going to finish off handout 4. So if you have handout 4, you'll want to grab that one. And I think I have a few extras if you were not here on Thursday. So if anyone needs an extra 4. Yep, and we're on the last quarter of 4. Thank you. Anyone else? Yes. Anyone? Yeah. Can you, anyone else needs an extra 4? Handout 4, because we're going to finish up the end of handout 4. Yeah, you can definitely have 4. Awesome. So we are going to finish this up by talking about memory. So there are actually a whole bunch of different ways that we can store data inside of our computer. So I am going to find my own handout 4, and there we go. Awesome. So I just want to make sure I am doing everything. Do you need a handout 4? You are good. Here you go. So what we're going to do is we're going to start talking about the actual memory, and there's a whole bunch of different ways we store data inside of our computer. And one of the first ways is going to be the very top of what I'm going to call the memory hierarchy. So basically, we're going to write out 6 different things, and this hierarchy, do you need a 4? Yeah, sorry. Yep, no problem. We're going to write out 6 different things, and they're kind of going to be organized as a triangle. I don't have the triangle drawn on your sheet, but you can kind of draw a triangle, kind of represent this hierarchy, because this hierarchy is going to go from things that are very expensive. So the very top is very expensive per megabyte. And then we're going to get cheaper and cheaper down to a very cheap per megabyte at the very bottom of this pyramid, of this hierarchy. And there's going to be an inverse relationship. Because things are very, very expensive per megabyte, we're going to have things that we list first as low capacity, and things that we list last as high capacity. And the idea is we want to discuss different ways we can choose to store data inside of our system. And the one thing we've already talked about is we've talked about the very first thing, this idea of CPU registers. So we said this was the actual thing that did the computation. When we actually looked at the source code, we saw a register named EDX and EAX, EBX. I don't know exactly which registers our compiler chose to use. But if you look back to the front side of 4, the last handout, you saw we had these register names, these EDX registers. There's very few of them. There's only about 16 to 32 of these registers, and they're only 64 bits each. So these CPU registers, or processor registers, they are very limited capacity. There's only 16 to 32 of them, and they're 64 bits each. So very, very, very small capacity, but extremely fast. We can access them in about 1 clock cycle. So if you have a 1 gigahertz CPU, you can access this a billion times every single second. So you can access this very, very quickly. You can access a lot of these registers. But they're very limited. They're very expensive to build. If we go down our hierarchy, we want to know where can we store even more data. And the second place we can store data is what's called the processor cache, or the CPU cache. It's our number 2 option. And when you look at the technical specification of your CPU, as you did for homework 0, you may have noticed that your CPU actually has something listed as L2 cache or L3 cache. So these are technical specifications that are listed about your CPU. And what this does is this gives us access to memory that's actually on the physical CPU chip. So it's on the same component in your computer as all the arithmetic processing unit that does the addition and subtraction and all the other circuitry. It's on that same chip. So it's very, very physically close to your actual registers. And in general, you have to put things inside your CPU cache before you can actually put them into your CPU register. So they're an intermediary between the system memory and your actual CPU registers. And the L2 cache, this is a cache per CPU core. So this is how much memory is on each actual individual core, because if you think of like 4 core machines, there's 4 actual individual CPU cores on a single chip, and each of those cores are going to have their own copy of the L2 cache. It's like a private cache for each CPU core. L3 cache is going to be the processor cache. There's only one of them. So even if you have a 64-core processor, you only have one L3 cache, even though you have 64 L2 caches. So you've got processor registers, and then which each CPU, each individual core has its own set of registers. Then they have their own set of cache, and then you have this globally shared cache. And caches are slower than your CPU registers, but faster than the third thing in our memory hierarchy, which is your actual random access memory, or the thing you call RAM. So this is our system memory. This is going to be where most of the data that we actually want to use ends up being stored. So actually going back to the CPU caches, I want to mention that these are in the size of probably about 20 megabytes. So just to give you an idea of how big a system cache is, we'll look at examples of particular processors in a second, but we're talking about 20 megabytes. So basically, if we think about 32 at 64 bits, we're talking about less than 1 kilobyte for the processor registers. We're talking about a few megabytes for the CPU caches. And on a given system, we have a lot of memory. In our dream computer, we have a total of, I think we had 128 gigabytes in this class. So we had a lot of memory inside our dream computer. Even my cell phone, I think, has 4 gigabytes in it. So a phone has, I'll say, 2 to 8 gigabytes, depending on kind of how new or how fancy of a phone you have. So you can see we've stepped up. We went from the kilobyte range to the megabyte range to the gigabyte range. That we're increasing capacity, and the cost per each megabyte is decreasing as we go down this list. And we can store data in any of these different places. So we're going to make a transition here between what I would call memory and what we're going to call storage. So at this point, everything we've talked about requires active power to maintain data. If you turn off power to your RAM, it loses all the information. Turn off power to the CPU, the caches are empty, the registers are empty. So then there becomes kind of this gray area of kind of things that are going to be fast, but long-lasting. So the fourth thing, the next thing you see on this memory hierarchy is going to be any sort of solid state, sometimes called flash storage or memory. Generally, we're going to refer to, so I'm going to say solid state storage is the common thing that you see most right now. So if any of you have built a computer recently, you're probably not putting an actual hard drive in it anymore, right? What do you want to put in a modern computer? Yeah, the M.2 drives. So have you seen an M2 drive? Yeah, so what do they look like? They're really small, and they're a chip, right? Yeah, they don't have any coding. They actually socket into this like little round hole onto your motherboard as a chip, and you kind of put it in this small little groove, and you kind of lay it flat. So it is actually a chip. It is flash memory that happens to be able to be have the resilience to actually store data without power. So this data is really, really fast. And typical M2 drives are in the range of, I'd say 200 gigabytes to like 1 terabyte. You can probably find an M2 drive that's even faster. If you're doing a little bit older technologies, you may have what's called an SSD. So SSDs are probably in the range of like 500 gigabytes to maybe like 2 terabytes or so. SSDs are sort of a slower version of these M2 chips. So we've got various different ways of storing data, and this storage is still pretty expensive per gigabyte, but there's more capacity. Yeah? Yeah, so memory is going to be everything. If we call it memory, we're generally refer to it as things that lose the data when the power's off. So your RAM is memory. But if you can store the data even without power, we generally call it storage. So anytime that's a hard drive, that data is there even if you've powered down your computer. So that's going to be something I'm going to refer to as storage. So if we go down the hierarchy one more level, the next option we can use is we can think about the actual hard disk storage. So these are the old school rotating disks. So these are often what you think of when you think of hard drives, at least if you are around people who have seen these old school hard drives. So the great thing is they still exist. You can still buy them. They're incredibly cheap. And they are generally you don't buy these kind of spinning hard drives unless you want lots of storage. So I'm going to say this is like 1 terabyte to maybe 500 terabytes. So you can get these spinning disks at low capacity, but if you're only needing a terabyte of space, just get an SSD drive. It's going to be just a little bit more and give you way better performance. But these are actual spinning disks that write them on this magnetic sheet. And they're really slow because they actually have to spin. You actually have to wait for the read cursor to actually get to exactly where your data is on that spinning disk. They usually rotate at like 5,400 RPMs. You can actually look up these disks, and they're going to have like a 5,400 RPM rotations per minute or 7,200 RPMs. If you're really fancy, I think they go up to like 10,800 RPMs. So these disks actually specify how many times the actual cylinder circle or cylinder plate rotates every single minute. So there's something that physically rotates, and it's writing it to a physical magnetic medium. So the great thing is lots of capacity, but very, very slow compared to everything else. And then the last form of storage that you are going to probably see is going to be some sort of high-density offline or tape storage. So I just say this is high-density storage. So number 6, and with high-density storage, you can think of this as any type of storage that you generally aren't going to always have available. So this is storage that might exist on tape records. So if you ever, so I worked at an investment bank for a couple of years while I was, before I got my PhD. And there's a ton of data you have to back up every single night. So even in the 21st century, they still had tape storage because these tapes are incredibly dense. So they have to write all of the stock transactions that they made and all the equity transactions and all of the over-the-counter transactions they made. And that has to be recorded and kept for multiple decades. So there's actually physical storage that actually happens with these tape storages. And once they write them, these aren't accessible. You can't go back and read this tape storage unless someone pulls the tape, actually installs the actual disk that has the data on it, and reads from that disk. So this is going to be extremely high capacity. We talk about a single one of these tapes are going to store greater than 1 petabyte of data. So massive amounts of storage per device, but they may not even be available when you need the data. You might actually have to physically request the data. So Amazon offers a service called AWS Glacier to provide this. So if you just need to store data for a really long time, log files, regulatory data, offline storage is a great mechanism. Incredibly cheap, but incredibly slow. And this is the 6 different kind of the hierarchy of memory and storage that we as programmers are going to get to choose where our data is located and how do we want to move our data around the computer. Because you're probably familiar with the idea that RAM is faster than hard drive and all of these different things. But I want to at least give you a bit of a foundation to kind of talk to you about sort of, we got these ideas of registers. We've got this idea of RAM. The RAM's going to have to move to a register. And in general, you're going to see that a CPU cache is going to be required. So data goes from RAM to cache, then cache to the registers. So data generally follows this pattern. That you don't ever write something directly from CPU cache to some sort of storage. You load that data into RAM first, then the RAM moves it to the CPU cache moves it to a CPU register. So the idea is we're going to take data that we don't know what data we want to access next, but we know that data is somewhere in storage. Whatever data we want to read, we read that storage into RAM. The particular part of RAM that we want to access in our CPU, we move it to the CPU cache. That goes into the CPU registers themselves. So this is just an overall view to get a bearings of where we're going. So what I want to focus on is really not storage. We're not even going to talk about storage at all anymore. If you want to store lots of data, there's ways to store it. You can learn about file systems and how file systems actually do it. We're not going to talk about at all how we're going to deal with storage. Instead, I want to talk about how we as programmers who are interested in building things and changing the world, how do we actually access things in RAM, and how do we make our programs run really fast? How do we keep data as close as possible? So any questions on the memory hierarchy? All right, let's see this in practice. Because what I love to do is I don't want you to sort of just believe me. I want you to see this actually happen. So I have a couple programs for you. So I have a program O4rc.c and O4cr.c. And I'm going to go ahead and bring up VS Code here. And we're going to look at these programs. And you have the key snippets about these programs on your sheet. So what is the difference between O4cr and O4rc? What differs between these two programs? Yeah, Aaron? Okay, so you're almost going a little meta. So we'll talk, so you've got this idea it's reading sequentially, but what's the actual physical difference in the program? Yeah, so the only difference between O4cr and O4rc is lines 16 and 17 are swapped. That's the only difference in the program. And to give you a little bit of context, what this program does, all it does is it basically allocates a really long array as size times an unsigned int. So I allocate a massive array of size times unsigned int. And this massive array that I allocate as size times unsigned int, I'm going to go ahead and just put data inside of this array. So I have this for loop that you see on your paper for I equals 0, for C is equal to 0, C is less than size, R is equal to 0, R is less than size. So all I do is create one big massive array, and I loop through that array to put data inside of that array. So the only difference between these two programs are lines 16 and 17 are swapped. Without running the programs, before we run them yet, what do we expect? Do we expect them to run in the same amount of time? They're the same program, right? They're doing the exact same functionality. I would say we would expect them to run in identical times, right? Or no? Seems reasonable, right? Same programs, exact same actions, exact same code, except for we've swapped 2 lines of code. I would think they should run in about the same amount of time. But let's go ahead and gcc O4rc.c. I'm going to run a.out. And this is size 25,000, so running a.out is just going to run it. But if I put the time argument right before it, so time space /a.out, it's actually going to track the amount of time that this program takes to run. So this is a nifty tool in Linux that I can see that the total amount of time it required to run O4rc was 2.77 seconds. So 2.77, I'm going to run it like 3 times. Is somebody writing this down? Can somebody be, are you writing these? Can you write down the 3 times? 2.77? And just 2.77, we'll just look at that. And I'll get it back from you in a second. So I'm going to run it a second time just to make sure we're not running a fluke. 2.55. And the third run of this program is 2.38. So there's going to be some variance depending on what else is running on my system and all sorts of other factors. So anytime you do an observation, you want to observe it multiple times. So we have 3 observations. And what was the approximate average? 2.5. So it took about 2.5 seconds for the CR program to run. So O4cr, I'd say the time it took is 2.5 seconds on average. Now I'm going to go ahead and gcc O4. That was, which one was this? This was CR, right? So I'm going to do RC. And I'm going to call it RC. I'm going to run ./rc, make sure it works. Looks good. Now I'm going to time ./rc. So now I'm running the other program that has a swapped for loop. And 2.74, uh-oh, this is not doing what I was, 2.8 and 2.79. So what do we see? What's the average of those three, approximately? About 2.8. So which program was faster? The first program. CR was faster. And so I'm going to do this test one more time because I was expecting a pretty extreme difference. And that's the joy of testing this on a different computer than this computer. And I'm going to go ahead and run this with, I'm going to run a.out, which is the first program. And I'm going to run it with 40,000. So I'm going to go 40,000 as the size of the array. So trial number 2, 40,000. Who can be my average keeper again? Who wants to average keep? Can you average keep? Okay, so 6.55. 6.43 and 5.62. So the average of those is probably what, like 6.1? Somewhere around there. And let's see about RC. So now we're doing an 8 GB allocation. And 6.5, okay. Yeah, pretty sure. So O4rc is RC. You were totally right. I thought I was going crazy. So we were running the exact same program. So GCC O4cr.c minus OCR. Okay, so column row is going to be, let's run time column row one more time. So now I'm back to the original one. So this is CR. Okay, so you had the original program, it ran in like, what was the original time that we said for both the original answers? What do you guys write down? 2.5 for the original program? For both of them, right? Was that what you guys get that too? Is that what we had? Yeah, so we had like 2.5. Okay, this makes me feel so much better. So for RC, for the second program, we were always running the second program. So we were always running row column. For when we do column row, when we do the first program, the first run took 11.1 seconds. The second program, the second time we ran this first program, it's taken a while. It's taken a while. 11.4 seconds. And if I run it a third time just to make sure it's not a fluke, we have 10.4 seconds. So the average of those, I would say, is about 11 seconds, right? So what we have is we've got two different programs that should be identical. The first program, the column row program, runs in about 11 seconds. The second program, the row column program, runs in about 2.5 seconds. That's a 4x difference in runtime. That's huge, right? What were you thinking? Or were you thinking something? I felt like I heard someone thinking something that was right on. Any thoughts on why this might have happened? Aaron alluded to a little bit. Yeah. Yeah, so it probably has to do with pulling from a slower portion of memory. So let's actually analyze what's happening with these programs. So when I run this O4 row column, what I'm doing is I'm allocating a massive array of a whole bunch of data, right? So I have an array, and it's a pointer to a whole bunch of individual integers. And let's say that I have a size of 4. So I have a size of 4. I'm going to have 16 total integers. And what I do is anytime you allocate something in memory, you are going to be able to index them by specifying where in the array we want. And I made a 2-dimensional array. So what I'm doing is I'm accessing it by the row times the size plus the column. R times size plus column. So basically, as I increment the column, I'm only moving by 1 address. As I'm incrementing the row, I'm jumping to the next row of my square, imagining this data as a square array. So what I can do is, instead of representing it like this, I can go ahead and say, I'm just going to think about my array as, even though it's a 1-dimensional array, because we don't really have 2-dimensional true arrays in C, even though it's a 1-dimensional array, I essentially have a size by size array. So I think of this as a 2-dimensional array, but remember, memory is always sequentially laid out. There's no such thing as 2-dimensional memory structure. All memory addresses are an individual number. So a 2D array is just a 1D array that's kind of looping around on itself. We can talk about these as rows and columns. So as we access each row and column, we can go ahead and say, for C is equal to 0, C is less than size. So if we start at C equals 0, then we say row is equal to 0, and we're going to go through all the different rows. So what I'm going to do is I'm going to access C0, R0 first. I'm going to access this element first. Then I'm going to jump down to the next row when I do column by row and access this data second, this data third, this data fourth, fifth, sixth, seventh, eighth. Does that make sense? How my access pattern is actually jumping down each row when I go column by row. So by jumping down each row, what's going on? Are these memory addresses between 1 and 2 next to each other? No. They could be really far off from each other. In fact, this is totally, if you had a size of 4, it's totally going to work just fine. But what I actually did was I had a size of 25,000. So 25,000, each of them are an integer. So 25,000 times 4 bytes is, I have about 100 kilobytes of data between the 2 different spots in my program. So what I'm doing is I'm accessing data here, jumping 100 kilobytes, accessing the next row, jumping 100 kilobytes, accessing the next row, jumping 100 kilobytes, accessing the next row, going through, and then at the very end, I've got to jump back several hundred megabytes to access the second column in the first row. So I am jumping around memory all over the place, going from one location to the next location to the next location. And by jumping around memory, we see that our system is really, really, really slow. But when we just swap these 2 lines, when we go we're going to complete each row, going column by column by column, what ends up happening is now we access 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. We have this nice sequential access of memory. We're accessing one element right after the next element. The thing we're accessing is right in the same order when we're running our second program. So this is an interesting observation. We see from a real system that if we're jumping around memory, it runs about 4 times slower than if we just access the memory itself. So does everyone see how this is actually slower and see what we observed? How just by changing the access pattern, we actually increase or decrease the running time of this program by a factor of 4. And the bigger and bigger the size of the array we make it, the slower and slower it gets. So this is really interesting. This can actually help us really save time in our programming and make data structures way more efficient if we make sure that we understand what's going on inside the system. So any questions on what happened here, or not exactly why? We'll talk about why next. But does everyone see kind of what the programs did and the fact that it was a difference in runtimes and why and the big difference between the access patterns of the 2 programs? And you can run these programs yourself, so you have all the source code online. Cool. All right, then at this point, we're kind of right between, so I'm gonna swap over here next lecture slides, and you can swap over to 5, and I promise we'll get caught up soon. So I have been looking at, so last night you guys, so on Friday night you guys finished up MP1, and how was MP1? Good? So do you feel like a little more comfortable with working with like kind of bit level and byte level operations in programming now? So hopefully you got a little refresher on pointers, because pointers are kind of something that if you don't have to deal with them, you kind of forget them. Yeah, Aaron? Oh, so like what's the best way, like for example, best way to do what? So like what's the cleanest way to access like an emoji, like check, okay, if the first character was, because we learned what did every emoji start with? F0, yeah. So you guys all figured out F0, and in fact, you guys probably all figured out it wasn't just F0 that it started with, but the second character is always 9F, right? So we know that every single emoji has these first 16 bits being exactly the same. So all of us together saw F0, 9F being the first 2 characters that we looked at, and then the third and fourth, or the first 2 bytes, and the third and fourth bytes are different. So one thing that I was looking through some of your code over the weekend and this morning before lecture, and I was looking at a number of your favorite emojis. So I saw a bunch of people's favorite emojis, and I had some favorite emojis. So one emoji is football. So whose favorite emoji was football? Say what? Oh, sorry. Sorry. I forget that this projector's weird. Sorry, football. American football, yeah, not soccer. So, oh, I'm sorry. I'll email them and be like, hey, I put your emoji up. I'm sorry I didn't see you. So second emoji. Oh my gosh, embarrassed face. Does somebody want to volunteer who that emoji was? Is that your emoji? Awesome. What's your name? Jake. Jake had embarrassed face, is that it? Oh, so it's more a surprise face on iPhone. I feel like you're looking up the emoji right now. Oh, so you had those, so you guys share the favorite emojis. Nice. So Monica, right? Monica and Jake. Emoji partners. That's awesome. So surprised. I'm guessing this is just what PowerPoint gives me or Google Slides. So this is the Windows version of the same emoji. So kind of maybe different expression. So that was one of mine. But then I saw some emojis that I was like, oh no. Was that yours? Oh, remind me of your name. Andrew, yes. So Andrew, why the mad face? So on the Apple, does it look less aggressive on Apple, or is it equally as raging? I don't know. Maybe you were feeling like Friday night, you were like, oh my gosh, I'm almost done, but I hate this MP. So this was I saw this and it's like, oh my gosh, I hope you're not too mad at me. And then another one, snowman. So whose favorite emoji is the snowman? Oh, hey, sorry. So what was your, so this was an interesting emoji because this wasn't a typical F-Zero emoji, was it? Nice. Yeah, so this, and remind me of your name? Rochelle, awesome. So Rochelle had this snowman emoji, and this snowman emoji was interesting because there's a few emojis that exist outside of the 1F000 to 1F899 range. This is actually just a 3-byte emoji. So I was actually looking through your source code. I didn't actually compile your codes yet. And I was like, oh, is this a real emoji? And it was like, yeah, that's a snowman. So this was a 3-byte emoji. I think it was like /EF was the first character. I don't know if you remember. Yeah, I think the first byte was EF, and then it had some other things. It wasn't like almost all of you guys chose the 4-byte emojis. But Rochelle, you chose a 3-byte emoji. So, and I love it. It's like winter is kind of coming. I don't know. I don't know if I'm happy about that or sad about that. So this is your emoji. We're gonna, so now we have all of your favorite emojis. So I'm gonna, as we work on so one of my goals for this class is at the end of the semester, we're gonna be building up to building microservices and building cloud scale solutions. So the final project for this course is actually that all of us are gonna build a microservice that is going to actually work together with everyone else's microservice. So we are building something bigger than our individual selves. So each of our services are gonna autonomously work with everyone else. So we're gonna build a massive cloud scale solution by the end of the semester. And now we have a fun way to represent each of you. I'm not sure what we're gonna do with like Jake and Monica, who are both the same emoji face. And I'm sure there's other conflicts in our hash table as well. But we'll figure that out when we get there. But we have basically a unique representation of all of us. So that was MP1. And I really wanted you to kind of get back into C programming, really understand byte level operations, and really see how understanding how things work deep inside the system is how systems programming works. It's understanding things at a very bit level and a byte level, and not being scared of those things, and understanding how we actually encode data in UTF-8. So you've become experts at this now. So for the second MP, you guys are working with PNG files. How's that going? Who has not started? Almost everyone, but there's a few people who have started. So definitely work on the PNG MP early, because the MPs are getting progressively more difficult. This one requires you to do a bit of reading of a technical specification. So there's a bit of understanding what a standards committee wrote about an actual specific format. And while it is, you don't have to understand the entire specification, it is a big document that you do have to really dive into to understand how a PNG file is structured. So don't wait too long, because the MP is due on Friday. see people skeptical of this. So, so due on Friday, and as, so I will kind of, and what I plan to do is I want to take a look, I'm going to take a look at all of your emojis. What I actually plan to do by Thursday is make sure that your grades get up on Canvas so you know exactly your grade, your final grade. And I'm going to compile a list of all of the emojis of everyone's favorite emoji, and we can see kind of what the distribution of the class looks like. As if each of you were an emoji, what does this room look like? And then I'm actually kind of interested in seeing like the distribution of what your random emojis you did was. Like how many of you guys actually used a blue heart as the emoji that you inverted? Any of you guys, one inverted blue heart? Oh, interesting. I think that'd be really cool to look at. I'm going to look at that. I want to see what the distribution of all the inverted emojis are. Cool. Any questions on the MPs or anything else dealing with class logistics? Yeah.
So I missed one of the lectures. What's the best way to catch up?
Yeah, you can definitely come by office hours. So the recording setup in here, so this building's great. It's pretty, it's new, it's shiny. But I guess the one thing they didn't get time to install was actual lecture capture. So any classroom in this building doesn't actually have any way to record anything by the classroom. So in all the other buildings, I basically just tell the classroom, hey, record this lecture. The classroom or some engineering IT person sets something up, the lectures get recorded, it just appears on either Echo 360 or whatever random video service the class or the university uses. This building doesn't have that. So I'm working on trying to figure, because I want to get this recorded, but I also want to make sure it's not total crap, because I actually don't think I'm recording. Oops. I'm not recording here, oh no. So what I'm trying to do is I'm trying to basically just record different things. So I can record this screen, and then we've got this recording of the screen. And the problem with this laptop recording is it only picks up the microphone on the laptop, which is total crap quality. You can barely hear it. There's also this computer that picks up if you look at this computer's camera, it is that guy right there. So it records this video, but it does pick up this mic. The problem is this camera basically sees just a tiny fraction of this screen and nothing else. So we basically get audio with crap video or video with crap audio. So yeah, Monica. Is it possible to post the? Yeah, that is a good idea as an alternative to the kind of actual lecture recordings. I feel like it does. I feel like actually working through the notes is actually helpful in learning. So I'm a little hesitant to that, but maybe until we get the video recordings, that's a good temporary solution. Does that seem fair? So I mean, my goal is, I think the dream is, so one of the things I want to do with this course long term is, if you Google, so you guys have probably Google searched some of this emoji stuff, and you were mentioning this, Aaron, a little bit, right? So you were Google searching around doing MP1 stuff. And is there really great, when you see these things, are you getting great Google results? The Google results for this kind of system stuff is kind of crap, right? Or even 225, when you were Google searching 225 stuff, what is the main website that you guys saw when you Google search 225 stuff? So some Stack Overflow. I'm actually seeing less and less Stack Overflow. Geeks for Geeks, yeah, I see a ton of Geeks for Geeks. How good is Geeks for Geeks? Yeah, it's okay at best, I would say, right? I would think we could do better, couldn't we? If we spent some time building our own Geeks for Geeks, do we think that Illinois can do better than Geeks for Geeks? Well, in terms of really good technical information on key CS concepts. So I think there's this weird divide. Like HackerRank and all the interview sites, like they actually do a pretty good job. They've got millions of problems. When I started up Problems a Day in 225, I wanted to kind of give you a HackerRank-like experience in that course. And I think, do you guys still do Problems a Day? Is that still a thing? Are they? Yeah, in 225. Yeah. So we created like 80 different problems that were kind of HackerRank-like problems, where you were able to just spend like 10 or 15 minutes to go through, and I think, and at least when I was running the course, we offered like 1 point of extra credit per problem of the day. And we capped it at like 40 points to make sure you didn't feel pressure to do all of them. Is that similar? Perfect. Okay. So I feel like that space is not a space that, like HackerRank's great, those sites are great, but I'm almost like imagining like we could have like a systems encyclopedia that's great results. So that may be something we try and build eventually. Because I think that's going to be the one thing that I feel like is a real weakness, is if you Google search a lot of the concepts we talk about here, you might get a Geeks for Geeks article that's okay, but I feel it's never great. And I think we could do great. And I think that's the problem with these recordings. I also want the recordings to be great. So I'm trying to like, great not be the enemy of good, but I think long term, that's where I hope that we can go, is we can hope to provide like resources that if you want to catch up, we've got the site that you can catch up on. And I think that's long term where we want this course to go, because I definitely know that that's kind of one of the weaknesses of the course for sure. I'm going to try and fix that somewhat this semester. So I'll try and get some posted notes for lecture 3 and 4. So you've got those. Did you miss 3 or 4? Just 3. Okay, so I'll get posted notes for that by tomorrow. Cool. Long tangent. Say what? Yeah, I'll get through. Everything doesn't have a video. Awesome. Anything else? Course logistics questions. Otherwise, is it going well? So far, so good. Okay. So then let's spend the last little bit of time we have together talking more about memory. I'm going to grab one of these guys because I can't. So what we're going to do is we have basically, before we start talking about the MPs, we have this idea that we have programs, and we know that O4rc, or CR, column row, that ran in like 11 seconds, right? Approximately 11 seconds is the runtime for the first program. And the second program, O4rc, row by column, ran in about 2.5 seconds. So there is this idea inside of a system that we have optimized the computer around the idea that we want to keep data close. So when working with memory in any computer, we want to access data as quickly as possible. We want the data to be as close to the top of that hierarchy. We want it to be as close to CPU registers as absolutely possible. And just to reinforce what we just talked about, a CPU register has only 1 word per register. And this idea of a word is a concept you're going to hear a lot in systems. And a word is just the length of the CPU architecture. So if you have a 64-bit CPU, that's going to mean your word is 64 bits. If you have a 128-bit CPU, a word on that CPU is 128 bits. So when you say a word in systems, that describes the number of bits in your CPU. So 64-bit processor, 1 word is 64 bits. And then there is only 16 general purpose instructions on x86 64. There's 31 on ARM v8. So if you have an M1 chip, you actually have a few extra registers. And these are your general purpose registers. There's a few additional registers, like a program counter is a register, but we don't count those because you don't just put random data in your program counter. So you have a few general purpose registers, that you can use on your system. And what we talked about below that is to put data in a register, we actually have to put it into a CPU cache. So I took a look at the dream computers that you guys wrote on homework 0, and a couple of you mentioned this particular Intel processor. You want an Intel i9-10900KF. So this is the i9 series, so these are generally the top-end gaming processors. And this CPU actually has 256 kilobytes of cache per CPU. And every single thing we do in the system, we're going to organize our data into what we call pages. So pages are going to contain 4 kilobytes of data. And this is a pretty much universal page size. That no matter what system you're on, if you're on a Mac, if you're on a PC, if you're on Linux, if you're on Windows, you pretty much organize things in 4 kilobyte pages. And when we talk about memory and moving data between memory, we're going to talk about moving pages at a time. We're actually not going to worry about moving a single byte at a time. We're going to move an entire page from disk to memory, or an entire page from memory into a CPU cache. So if we look at this, we have an Intel i9 processor. It's got 256 kilobytes per CPU, so 256 kilobytes divided by 4 kilobyte pages. So we have, what, 64 pages? So in our actual CPU, we have 64 kilobytes per CPU, or sorry, 64 pages per CPU. Then we have 20 megabytes of extra cache that's shared between all of our CPUs. So how many pages is that? Well, we can do that by simply taking 20 times 2 to the 20th, dividing by 4 times 2 to the 10th. So that's going to be 5 times 2 to the 10th. So that's going to be 5 kilobyte pages. So 5 times 1024. Is that right? Yeah, seems good. So we have 64 individual pages, and then we have 5 kilobytes worth of pages shared between all of the processors on our CPU. So we don't have that many pages on our CPU. So we basically have 5,000 and some places to put data inside of our CPU. And then if we think about RAM, how many pages do we have in RAM? So in our dream computer, we said we had 128 gigabytes of RAM. So if we have 128 gigabytes of RAM, 128 gigabytes, so a gigabyte is 2 to the 30th, so 128 times 2 to the 30th, divided by 4 times 2 to the 10. So that's going to be 32 times 2 to the 20th. So 32 megabytes of pages in RAM. So the way we organize our system is we're going to organize all of our memory into pages. These pages are 4 kilobytes in length, and these pages are going to move between our disk into RAM, and in RAM we can store 32 million of them, and then into our CPU registers where we can only store about 5,000 of them. Yeah? Are there what? Are the units okay? What do you mean? Yeah, you can have megabytes of pages. So here the unit is, I mean, if you want to be more precise, this is just, I'm using megabytes because this is 32 times 2 to the 20th pages. I mean, maybe the byte, I guess you're, yeah, maybe you're more tech, I think that's what you're pointing at. The bytes is probably wrong. Yeah. 24 mega pages, that's, I think you're technically correct. That you're right. That this should be, they're not megabyte pages, they're mega pages. but 32 times 2 to the 20th. So we don't have that many pages. We only have 32 million spots in our dream computer that has a lot of RAM into it that actually we can store data. So what we have is there's a key idea in computer science that we've developed around this idea for the past 50 years. And that idea is called the principle of locality, or locality of reference. And this is a principle that a program will access the same small region of memory over a short period of time. So this is a principle that most programs follow. It's not an absolute rule, it's a principle. And if you look at the execution of most programs that people program, it's going to access the same set of pages, the same set of memory, repeatedly over a small period of time. So if you think about what you've programmed before, you've probably written a lot of for loops, and inside those for loops, you've probably accessed a few different variables inside those for loops. So while your program's running that for loop, it's accessing that same region of memory of whatever variables are inside the for loop. And that is how most programs end up working. So most programs follow this locality of reference or principle of locality idea. That it's going to access the same amount of memory or the same memory over a short period of time. So what we've done is we have optimized our entire computer system around this principle. So everything we do is based around the idea that we expect a program to access the same memory. So let's see actually how we've designed systems to do this. So to do that, I want to first introduce a few simple terms. So we are all familiar with the third level of our hierarchy, or system RAM. You all found out how much RAM you had on your dream computer. And all computers have a fixed amount of RAM. So the great thing about RAM is sequentially ordered. So RAM is sequentially ordered. It basically starts from 0, OX0000, and goes all the way up until OFFFFF, until you're out of actual RAM. So you have this sequentially addressed space. The very first byte of RAM in your system is 0. The very last byte of RAM is going to be all of the biggest number until you're actually out of RAM. System RAM is not just sequentially addressed, but it also is shared. So physical RAM is a single resource shared between all programs. So physical RAM is a single resource that's shared between all of your programs. And what we want to do and we're going to say this is managed by the operating system, by the OS. We're going to talk about how it's actually managed later. But the physical RAM, the physical chips of RAM, they have addresses from 0 to FFFFF, and every single process is going to use the same physical RAM. There's not different physical RAM for each different process. Everything that's running on your computer is sharing that same physical RAM. The third thing to learn about for physical memory is, as an app programmer, we never see a physical memory address. Every single memory address you see in every single program you've ever programmed is not the address where it is physically on RAM. You will, as a programmer, unless you do kernel development, which you can do if you take like a course like 423, but unless you do kernel development, everything you see is not a physical address. We will never actually see the physical address because it is freakishly dangerous if all of your programs can see all of the RAM on the system. Because we don't want you to have access to all of the system's RAM because other people are on this computer. So you never, never, never see a physical memory address. If you have an address up pointer, that's not the physical memory address. So I mentioned earlier, I probably should have this slightly earlier in the slides. On whole organized RAM, we break it up into chunks called pages. We've talked about pages. And we can actually find out how big a page is on Linux by actually running a git-conf command and looking at the page size. So if I go over here and do git configuration, page size, I can see that on my system, I have 4096. So this is exactly what I expect to see, that this is 4096, which is 4 kilobytes. So what we said was we don't want all of our programs to access the same memory at the same time. That seems crazy dangerous. So instead, on every modern system, we're going to have an abstraction called virtual memory. So virtual memory is this beautiful abstraction between physical and virtual memory addresses. So everything we've seen is never a physical memory address. Instead, all you ever see is a virtual memory address. And virtual memory is this idea of how do we take a physical memory and abstract it into a virtual memory, which we can give to each process. And this is done through this magical structure called a page table. So a page table translates a physical address into, the page table translates, a virtual address into a physical address. So a page table, you can have a virtual address. The virtual address will translate the virtual address into a physical address. And the beautiful thing about a page table is a page table is not shared. Every process has its own page table. So every single process has its very own page table. If we were all processes running inside a computer, I have my own page table, you have your own page table, you have your own page table, you have your own page table. Yeah. Yes. Yeah, the operating system, well, it's kind of, the CPU and the operating system work together to make a page table. Where are page tables stored? They are themselves stored in memory, but they're going to be stored in memory that the kernel is going to control. So we can basically, to store a page table, there's a clever little hack that I don't know if we'll get into this semester, but you actually only need one page of memory to store an entire page table. Because you'll end up having a multi-level page table where you basically have pointers to other page tables. But we've got this magical structure that's going to be stored in memory that allows us to translate for every single process, a process virtual address into its physical address in RAM. And the reason we do that is to kind of go through the very last example I want to go through. And this is a very massive screen of a huge table. And we're going to assume that we are in a system that has just 16 pages of RAM. So we're in a very, very memory-constrained system. And in this system, we're going to do a series of operations. So we've got 3 processes running at the same time on the system. They each have their own page table. The first command I see ran is I see process 1 runs on the CPU, and it runs the command a equals malloc of 3 times 4 kilobytes. So what this means is the process A wants 3 pages of memory. So what I'm going to do is I'm going to go ahead and go to process 1 and give the variable A 3 pages of memory. And then I'm going to return the address on this page table. So this address is OX1000. So the result of this call is A is equal to OX1000. After this is called, A has a virtual memory address. And then we also need to stick this in memory somewhere. So all the page table does is the page table essentially has a pointer that says this points here, this points here, and this points here in RAM. So now we've translated a virtual address to where it's physically stored in RAM. The page table is basically just a giant table of pointers. Yeah? So is there a reason we skip the first slot? Yes, because as a rule, we never use the address 0 because we don't want null to actually be a valid memory address. So memory address 0 should always never be used in a virtual page table. And I just wanted to be technically correct here. So second line is B. B is equal to malloc of 5 blocks, or 5 pages, on process 3. So 1, 2, 3, 4, 5. I'm going to have B. And then B is going to go ahead and point to the next 5 blocks of RAM. So now I've used 8 blocks of RAM, but what is the memory address that process 3 has for B? What is B's memory address that we return? What's the beginning of chunk B? It's 1 page into the system, so that memory address is 1000 as well. So right now, at this point in our program, A has memory address 1000, right? B also has memory address 1000 in process 3. So both A and B have memory address 1000, but they are pointing to completely different physical memory because every single virtual page table is private. So even though process A and process 1 and process 3 both have something that's at memory address 1000, those are completely different memory address 1000s because we use a virtual page table to translate them. I'm going to go through just 2 more of these. So process 1 then allocates C to be equal to 2 times 4 kilobytes. So I'm going to just go ahead and put it right here on its heap and say variable C goes in the next 2 slots. But now these have to be mapped further down in RAM. So something interesting just happened here. In the term, and then if we return the value, we can now say that C is equal to the memory address 4000. Because the beginning of block C is that address 4000 inside of that page table. It's 4 blocks in. So from the point of view of a programmer, is A and C sequentially in memory in virtual memory space? Yeah. So it looks like you've just allocated A, then allocated C. Looks to you as a programmer that you've got A's memory, you've got C's memory. In reality, are they next to each other in RAM? No. After you finish reading A, you actually then, the next byte of data inside RAM is actually process 3's data. And as a final thing, what happens when we do that? What happens when we access process 2's data or process 3's data? If we were to actually do that, if we were to access a page, or, well, if we were to access a page that wasn't ours to access, So if process A was trying to access like some address down here that's not translated, this itself is a page fault, or is a segmentation fault. So on Thursday, we're going to continue with this example and actually talk about where seg faults come from, how they occur, and how the virtual page table allows us to organize a whole bunch of memory from a whole different bunch of processes really, really simply. So we're going to pick up here exactly where we left off. And I'm going to try and get caught up on the handout. We'll have a short handout, number 6, so we can be completely caught up and stop using the previous lecture's handout. So make sure to bring back handout 5. I'll be here after class if you have any questions. Otherwise, have a fantastic couple of days, and I'll see you on Thursday.